This is video 3 for the statics unit. So in this one we're going to begin by talking about friction. I've mentioned friction in the past, and we can use it, but now we're really going to dive in and say, try to take a look at what friction actually is. Now this is a contact force that happens to be parallel to the surface that we have. It has to be caused by two objects, and again we got friction. Friction opposes sliding. That's very important to remember. Friction always opposes sliding. What causes it is these microscopic peaks and valleys. So, for instance, if I take a look at like a blown up view between a box and, let's say, a floor, there would be these tiny little peaks and valleys that can line up. That's what causes friction. And it is an electromagnetic thing. If we dive even deeper, we can see that it actually comes from the atoms being attracted to each other, kind of like a London force or a van der Waals force or something like that. So the first type of friction we have is static friction. Now, these friction forces, they're complicated at that microscopic level, and it is still an active field of research. But we do have some models. So in the simplified one, the maximum magnitude of a friction force, it's going to be proportional to the normal force. So the static friction, which I like to use a script F, and the maximum static friction that I can have is proportional to the normal force. We use this alpha symbol for proportionality. What that means is that this friction will equal some constant times the normal force, and that's a constant of proportionality. So that's what we need to find. Now, with static friction, if you think about it, if you push on something, you can push harder and harder and harder, and it will stay in place. So static friction is a variable force. It changes. It always matches how much force you push on the object. That is until you break it free. So that's the maximum static friction that's possible. All right, so going back to this constant of proportionality, for friction, it's called the coefficient of static friction. We use the mu symbol, which looks like a U with a tail in front. And that's how we can calculate the maximum static friction. Now, if we do just a little bit of math, we see that the coefficient is a ratio of the static friction to the normal force. And because this is a ratio, it is unitless. So mu will always be unitless because it's a ratio. All right, now if we take a look and make a graph of the friction force versus the applied force. So the applied force is if you start pushing on something. So for example, if you're pushing on something, you are giving an applied force, and then the friction is going against you. So we would see a linear relationship between static and the applied force, right up until we get to a threshold. That's where we have the maximum static friction possible. Now, from your experience, you may have noticed this. Once you break an object free, it's easier to push or to keep it moving than it was to break it free. That leads us into kinetic friction. And notice that kinetic friction, which is represented by this line right here, is less than the maximum static friction. The physical reason for that is because once you break those peaks and valleys free, it's just easier to keep breaking them free than it is to let them, if you stop and let them reestablish. So for kinetic friction, this time it's weakly dependent on speed, but it's still roughly proportional to the normal force. So once again, we see this relationship here. And that's really, really nice. You only have to know one formula for both static and kinetic friction. But what you have to remember, though, is that the coefficient for static friction is always greater than the coefficient for kinetic friction. So on a horizontal surface, a larger force is required to start an object than it is required to keep it moving. Another type of force I'd like to discuss in this video is springs and elastic cords. And this gives us a great example of how a force is an interaction between two objects. So here I have two objects interacting, and the medium that they're interacting through is the spring. Now, as you pull on a spring, the spring pulls back on you with an equal force. As you pull farther from that rest, from the spring's rest position, the force becomes greater and greater. Now, obviously, there's going to be a point, if you pull the spring too far, the spring will become damaged. But before it becomes damaged, there's this nice relationship. Now, we call this a mass spring system. So what I can do is I can set up an apparatus where I can put varying masses at the end of a spring, and I can measure its displacement, and I'd reference it back to its rest position. So what I want to do is I want to make a graph of the force versus displacement, where displacement is final position minus initial position. And the initial position will be the rest length of the spring. Now, I found some data online, and basically for the forces, which was measured in newtons, and then displacements measured in meters, there was a lot of data. Now, as you might imagine, if the force is 0, then the displacement 0. I'm just going to put down some of these data points. There was more data points. There's quite a lot of them. Well, what I'm going to do now is I'm going to plot the force on the y-axis, and I'm going to plot the displacement on the x-axis. And when I did this, I saw a nice linear relationship. Now, remember, whenever we see a graph, we want to understand what the slope represents and what the area represents. So for the slope, the units would be a Newton divided by a meter. Now, that doesn't have any meaning to you just yet, but we're going to learn that that's actually the spring constant. The area would have units of newtons times a meter. And again, this has no meaning to you yet, but we're going to learn later in the year that that is actually a unit of energy. So the area would represent like the potential energy we're storing in the spring by stretching it. Now, I went through and I calculated the slope. And I got a slope of 22.5 newtons per meter. So the spring constant for this graph was, for this spring was 22.5 newtons per meter. Now, since this force is proportional, since we had a nice linear line, the elastic force will be proportional to the displacement. So that means then we must have some force, the elastic force must equal some constant times the displacement. And the person who saw this was a scientist named Hooke, and he saw that, hey, this is true for many, many different springs. So this became Hooke's law, where we have the elastic force equals the spring constant, which we represent with a lowercase k, times the displacement. Now, force is a vector, and displacement's a vector. And if you think about it, the force vector will always point in the opposite direction as the displacement. So think about if you hang something from a spring, its displacement is in the negative y direction, but the elastic force is pointing up. So that means that we need to include a minus sign to complete that model. All right, so once again, k is called the spring constant. We can find that by finding the slope of our graph, newtons over meters. The minus sign, again, is because the elastic forces, we call them restoring forces. The elastic force is constantly trying to restore the spring to its rest position. It's constantly trying to pull it back to that rest position. So it always points in a direction that is opposite to the displacement, because the displacement comes from an applied force. Now, if we were to continue with our graph, we have two regions. First off, we have the elastic region, which is right about here, back to the origin. This is where Hooke's law works. Once we get past the elastic region, we enter the plastic region, and now it's no longer linear. So Hooke's law will not work in the plastic region. And then obviously if you pull it too far, you can break the spring altogether. And that concludes video 3.